Quasi-hereditary algebras, lecture 7, examples, regular monoids. Let us start by recalling the definition of a monoid. A monoid is a triple which consists of a set S, a binary operation dot on S, and a fixed element E in S. This datum should satisfy the following axioms. The operation dot should be associative, meaning that A times the product of B and C should be equal to A times B times C for all A, B, and C in S. The second axiom is that our fixed element E should be a unit element or an identity element in the monoid. And this means that A times E is equal to E times A and is equal to A for any element A in S. Here are some examples. We have the monoid of all non-negative integers with respect to addition and with the identity element being 0. For any field K, we have the monoid of all n times n matrices over K with respect to matrix multiplication and with the identity matrix of size n being the unit element. Also, for any set X, we have the monoid T of X of all transformations of X, which means all maps from X to X, with respect to composition of maps, and with the identity map being the unit element. Basic structural properties of monoids are described by the so-called Green's relations. Let S be a monoid. In what follows, we quite often use the notation S instead of S, dot, E, and we will also simply write AB instead of A dot B. For two elements A and B, we will write A, L, B, provided that the left ideals generated by A and B in S coincide. We will write A, R, B, provided that the right ideals generated by A and B in S coincide. And we will write A, J, B, provided that the two-sided ideals generated by A and by B coincide. We will write A, H, B, provided that A, L, B and A, R, B. So in this way, we define binary relations L, R, J, and H on S. A little technical lemma says that the binary relations L and R commute as binary relations. So we have the semigroup of binary relations. Any binary relation on a set can be seen as a matrix whose rows and columns are indexed by the elements of the set and whose entries are 0 and 1. And 0 and 1 are exactly the elements of the Boolean semiring. So we have a 0, 1 matrix. So a matrix with coefficients in a semiring, we can multiply such matrices. And if we have two equivalence relations L and R, it turns out that they commute with respect to this multiplication. As a consequence, their product, it doesn't matter in which order we take this product, their product is again an equivalence relation. We denote it by D, and this is a minimum equivalence relation which contains both L and R. So these binary relations L, R, J, H, and D are all equivalence relations on S, and they are called Green's relations. The definition of Green's relations admits a very natural generalization. Given two elements A and B in S, we can write that B is L greater than A, so left greater than or equal to A, provided that the left ideal of S generated by B is contained in the left ideal of S generated by A. Similarly, we write that B is right greater than or equal than A, provided that the right ideal generated by B is contained in the right ideal generated by A. And finally, B is two-sided greater than or equal to A, so J greater than or equal to A, provided that the two-sided ideal of S generated by B is contained in the two-sided ideal of S generated by A. Then these three binary relations are partial preorders, which are usually called the left preorder, the right preorder, and the two-sided preorder. And the equivalence classes with respect to these preorders are exactly our equivalence relations L, R, and J. Also, terminological remark, the equivalence classes of Green's relations are sometimes called sets. So we can talk about left cells or L cells, right cells or R cells, two-sided cells, so J cells, D cells, and H cells. And all this originates from the paper by Sandy Green, which has title On the Structure of Semigroups and which appeared in 1951. Next, let us discuss idempotents and maximal subgroups in monoids. So let S be a monoid. Let us denote by E of S the set of all idempotents in S, that is, of all elements F in S, such that F squared is equal to F. Please note that the identity element E is an idempotent, so it belongs to E of S. A little technical proposition. If you have an element F in E of S, so if you have an idempotent F in our monoid S, then the H class of this idempotent, so the class H sub F, which consists of all elements S in S that are H equivalent to F, is the maximum with respect to inclusions subgroup of S with identity F. And another proposition, if you have a finite monoid S and two idempotents F and G in E of S such that F and G are J equivalent, then the corresponding maximal subgroups H sub F and H sub G are isomorphic. A typical example, the group H sub E, so the maximal subgroup for the identity element E, is the group of all invertible elements in S. That is, all elements S in S, for which there exists some element T in S, such that ST is equal to TS and is equal to the identity. Let us look at more detailed example. Let's look at Green's relations for the semigroup Tn of all transformations of the finite set and underlined, which consists of all elements 1, 2, 3, and so on up to n. Let us also note that we compose transformations as functions, that is, from right to left. For each element sigma in our transformation semigroup Tn, we can define its image. So its image is a subset of n underlined, and it consists of all elements sigma of x, where x is an element in n underlined. Then we have the kernel of sigma. The kernel of sigma is the equivalence relation on n underlined, which is given as follows. Two elements x and y are ker sigma equivalent if and only if sigma of x is equal to sigma of y. And we have the rank of sigma. The rank of sigma is the cardinality of its image, or equivalently, the cardinality of the quotient set of n underlined modulo the kernel. Then here is a description of Green's relations for Tn. Two elements sigma and tau in Tn are right equivalent if and only if they have the same image. They are left equivalent if and only if they have the same kernel. They are two-sided equivalent if and only if they are D-equivalent, if and only if they have the same rank. And they are H-equivalent if and only if they have both the same kernel and the same image. So this allows us to describe idempotents and maximal subgroups in Tn. An element sigma in Tn is idempotent if and only if, for any equivalence class of its kernel, we have that sigma sends the whole equivalence class to some element in this equivalence class. Consequently, every left and every right cell of Tn contains at least one idempotent, because for any equivalence relation on an underlined, each equivalence class contains at least one element. So we can send this equivalence class to that element and thus construct an idempotent with this kernel. Of course, if there are equivalence classes that contain more than one element, then we will have more idempotents in those left and right equivalence classes. The H cell of an idempotent sigma consists then, of course, of all bijections between the classes in the kernel of sigma and the elements in the image of sigma. So this means that the maximal subgroup of Tn with identity our idempotent sigma is isomorphic to the symmetric group on rank sigma elements. In particular, we see that two idempotents are J equivalent if and only if their ranks are the same as we saw in the previous slide, if and only if the corresponding maximal subgroups are isomorphic. Okay, next let us discuss the notion of regular elements. Let S be a monoid. Definition: an element A in S is called regular, provided that there is an element B in S such that ABA is equal to A. So this definition is a little bit asymmetric, but this can be improved. Let us set B prime to be the element BAB. Then, assuming that ABA is equal to A, AB prime A is equal to ABA BA, which is equal to A because ABA is A. And also B prime AB prime is equal to BAB times A times BAB. So we can remove one ABA to make it into A, and then the second one, and we get BAB, which is B prime. So if we have an A for which there is a B such that ABA is equal to A, then there is also a B such that both ABA is equal to A and BAB is equal to B. So this makes the definition a little bit more symmetric. For example, any idempotent is a regular element. Definition: a monoid S is called regular, provided that all elements of S are regular. And here is the main lemma which describes regular elements. An element A in S is regular if and only if it is D-equivalent to an idempotent, to some idempotent F. Corollary: the monoid Tn is regular. As we saw, each J class of Tn contains an idempotent, which means by this lemma that Tn is indeed a regular monoid. So let us prove our lemma. So assume that ABA is equal to A. Then, multiplying with B on the right or on the left, we see that both AB and BA are idempotents. Since A is equal to ABA, AS is equal to ABAS. This is, of course, included into ABS, and this is included into AS. So we have that ABS is equal to AS, and hence AB is right equivalent to A, which means that AB is D equivalent to A. So our element A is D equivalent to an idempotent AB. Conversely, let us assume that we have some element A which is D equivalent to some idempotent F. This means that there is some element D such that A is left equivalent to D and D is right equivalent to F. That's because the Green's relation capital D is the product of L and R. Then, in this situation, since A is left equivalent to D, we can write A as xD and D is YA for some x and y. And since D is right equivalent to F, we can write F as DU and D as FV for some U and V. Consequently, we have that A is equal to XYA and D is equal to DUV, and also that F is equal to YAU from these equalities. Now, the fact that f is an idempotent means that f squared is equal to f, and since f is yau, this is equivalent to yau is equal to yau. We can multiply this with x on the left and with v on the right, and we get xy au yauv is equal to xy auv. But we also see here that d is equal to duv. So ya, which is d, is equal to yauv. So we can simplify this simply to ya, and xya is equal to a. So the right-hand side simplifies to a, and the left-hand side similarly simplifies to a times uya. And this means exactly that a is a regular element. This completes the proof of the lemma. Now we can talk about cell modules over monoids. Let K be a field. So we are interested in the monoid algebra K of S of our monoid S over our field K, and the corresponding category of finite dimensional Ks modules. Let L be a left cell in S. Let us consider its linearization, so the formal vector space where the elements of L form a basis. For any element A in S, we can define the linear action of this element A on this linearization K of L by prescribing the values of this action on some basis element V in L as follows. So A applied to V is equal to AV if AV is an element in the left cell, and it is equal to 0 otherwise. We claim that this defines on K of L the structure of a K of S module. So this module is called the cell module, which corresponds to the left cell L. Let's prove this lemma. What we need to prove the associativity of our multiplication. So A applied to B of V should be equal to AB applied to V for all AB in S and V in L. If both BV and ABV belong to L, then this formula follows from the definitions and the associativity of the operation on S. If the element BV doesn't belong to L, then the left ideal of S generated by BV is strictly contained in the left ideal of S generated by V. In particular, the left ideal of S generated by ABV is strictly contained in the left ideal generated by SV, which means that ABV does not belong to L. But then by definitions, it follows that both sides of our equality are equal to 0, and so the equality holds. If the element BV belongs to L, but the element ABV doesn't belong to L, then similar arguments show that both sides of our equality are equal to 0. And this proves our lemma. Now let us list some auxiliary facts and lemmata. Fact 1. If S is a finite monoid, then the Green's relations J and D coincide. Fact 2. If S is a finite monoid, then all left cells inside some fixed two-sided cell are left incomparable. And similarly, all right cells inside some fixed two-sided cell are right incomparable. Lemma: if some D cell D contains an idempotent, then any left and any right cell in D contains an idempotent. So this follows directly from our proof that any element that is D equivalent to an idempotent is regular. Lemma 2: if L1 and L2 are two D equivalent left cells, then the corresponding cell modules are isomorphic as Ks modules. Proof: since the relation D is a product of the relations L and R, for any element A in L1, there is some element B in L2 which is R equivalent to A. Let x and y be two elements in S such that ax is equal to b and by is equal to a. So they exist because a and b are equivalent. Then we have two maps, right multiplication with x, and this is a map from L1 to L2, and right multiplication with y, this is a map from L2 to L1. From these equalities, it follows that axy is a and byx is b, which means that these two maps are actually mutually inverse bijections. These maps are given by right multiplication. This is certainly commutes with left multiplication, and left multiplication describes on cell modules the structure of a KS module. So these mutually inverse bijections define isomorphisms between our cell modules KL1 and KL2. Next, we need to talk about the notion of an apex. Let S be a finite monoid and V a simple module over the corresponding monoid algebra. Lemma: there is a unique two-sided say J, of course it depends on V, such that for any element S in S, the fact that S does not annihilate V is equivalent to the fact that S is two-sided less than or equal to our J cell J. Moreover, this cell J is regular, which means it contains an idempotent. So this J cell is called the apex of our module V. Proof: if I is an ideal of S, then, since our module V is simple, applying the linearization of I to V, of course, gives a submodule, and so this submodule is either 0 or the whole module V itself. Now let us take a minimal ideal I with the property that k of I times V is equal to V. Due to the minimality of I, if we look at all two-sided cells which are contained in I, the ideal I contains a unique minimal two-sided cell with respect to the two-sided order. Because as soon as we take some smaller ideal, our property KIV is equal to V should fail. So this is given by some unique minimal two-sided cell in I. So if you look at our two-sided cell J, which we just defined, then applying its linearization to V gives V, because all other two-sided cells in I applying to V give 0. So we claim that our two-sided cell J is the apex of V. Indeed, if it is not the apex, if it's not unique, then there is another two-sided cell J prime, which is unrelated to J in the two-sided order, which has the same properties as J. If we multiply J and J prime, the fact that they are not related in the two-sided order means that their product must be strictly two-sided greater than both J and J prime. But then this should kill V, because of the minimality property of both J and J prime. But at the same time, K of JV is equal to V, and K of J prime V is equal to V. And this gives us a contradiction. Also, the fact that K of JV is equal to V implies that K of J times K of J, V is equal to V, and this means that J is contained in JJ. So it is a regular two-sided cell, and so it must contain an idempotent. And this completes the proof of the lemma. Now let us discuss cell modules as bimodules. Let S be a finite monoid, and L be a regular L cell in S. Let F be an idempotent in this left cell, L. Then, multiplying L with F on the right gives us L. This is because F squared is equal to F. And hence, multiplying L on the right with any element in the H cell of F gives us our left cell back. This means that our cell module KFL is naturally a bimodule, where the left action is the action of K of S, our monoid, it's given by left multiplication, and the right action is the action of K of HF. So that's a maximal subgroup for our idempotent F. And this action is given by the right multiplication. So in particular, this gives us a functor. We can tensor with our bimodule K of L on the right over K of HF. And this gives us a functor from the category of all modules over our maximal subgroup H of F to the category of all modules over our monoid S. And a piece of notation for an idempotent F in S, we denote by L sub F the left cell of S, which contains F. Now we can formulate the theorem, which is due to Mann and Poniatowski, which classifies simple modules over finite monoids. Let S be a finite monoid, and K an algebraically closed field whose characteristic does not divide the cardinality of any maximal subgroup of S. Then, for any idempotent F in S, and any simple module V over the corresponding maximal subgroup HF, the module obtained from V by tensoring with the bimodule KLF has simple top. We denote this simple top by Q, and it depends on F and V. So it's Q of F and V. The apex of this simple module is the two-sided cell which contains F. Next, two modules QF, V and QF, V prime are isomorphic if and only if V is isomorphic to V prime. So here V and V prime are simple HF modules. Next, if we have two idempotents F and F prime in S that are J equivalent, and then if we add up all modules of the form QFV for the first idempotent F, and all modules of the form QF prime V prime for the second idempotent F prime, then these direct sums will be isomorphic as S modules. And finally, any simple S module is isomorphic to QFV for some F and V as above. This theorem gives complete classification of simple modules over finite monoids. Here is the idea of the proof. Consider our cell module KL as a bimodule. It is a left module over our monoid S, and it is a right module over the maximal subgroup of S, which corresponds to the idempotent F, and F is some idempotent in L. So this module KL, it's easy to see that it is free as a module over our maximal subgroup. Therefore, when we tensor our simple module V with this bimodule KL, this produces a module which has a distinguished KHF submodule which is isomorphic to V. There is a unique component here which is responsible for transferring the KHF structure. So this module V survives in any non-zero quotient of our tensor product, and this implies uniqueness of such quotient and proves the first assertion of our theorem. The fact that the apex of our module QFV is the J cell containing F, this follows directly from the construction. If we have two non-isomorphic simple modules V and V prime, then the fact that QFV is not isomorphic to QFV prime follows by noticing that the module QFV does not contain a submodule over our maximal subgroup, which is isomorphic to V prime, while the module QFV prime does contain such a submodule. If we have two-sided equivalent idempotents F and F prime, then the isomorphism which we had here between these direct sums of the corresponding simple modules This isomorphism follows directly from the isomorphism of the cell modules, which correspond to F and F prime, which we mentioned a couple of slides ago. Finally, let T be a simple S module, which has some apex J. Note that we know that J is a regular two-sided cell, so it has some idempotent F. And then, if we look at the cell module which corresponds to the left cell of F, then sending our idempotent F, it's also an element in the cell module, to any non-zero element in the image of F acting on T, and this is well defined because F belongs to the apex of T. So by adjunction, this gives a non-zero homomorphism from our cell module to T. And therefore, T is a quotient of our cell module, and thus of some QF of V. So here, in this argument, we in particular use that the group algebra of our maximal subgroup over K is semi-simple. So the regular representation of the maximal subgroup is a direct sum of simple modules. So this splits our KLF into the direct sum of modules isomorphic to tensoring our cell module with some simple module V over H. Now we are ready to formulate our main theorem. Theorem, it is due to Mohan-Puccia. Let S be a finite regular monoid, and K an algebraically closed field whose characteristic does not divide the cardinality of any maximal subgroup in S. Then the monoid algebra of S is quasi-hereditary with respect to any linear order on the set of equivalence classes of simple modules, which extends the two-sided order on the apexes of the simple modules. And the standard modules for this structure will be exactly our modules capital F sub little f applied to V. So we start with V, and then we tensor with the corresponding cell module over the maximal subgroup. This theorem was proved by Puccia in his paper in Journal of Algebra in 1998. So here is the proof. So we need to prove that these modules are indeed standard modules for this quasi-hereditary structure. For this, we need to prove two things. First of all, that this standard module surjects onto a simple, and the quotient is filtered by strictly smaller simple modules. So our standard module, capital F sub f applied to V, has exactly one copy of V as a module over the maximal subgroup. And this copy survives in the simple quotient QFV. So this means that the multiplicity of QFV in our standard module is 1. And the kernel of the projection from our standard module to our simple module is killed by the idempotent F by construction. Therefore, any simple in this kernel has apex which is strictly smaller than the apex of our simple module. And this proves exactly 1/2 of our theorem. Now we need to prove that all projective modules have standard filtration, which is directed in the correct way. So let L1, L2, and so on Lk be the list of all left cells in A, which is written such that Li is left bigger than Lj, implies that the index I is greater than the index j. Let Ni be the linear span of all Lj's, where j is greater than or equal to I. And of course, the linear span inside the left regular module. Then we have a filtration. So 0 is a part of Nk. This is a subspace in Nk plus 1, and so on, all the way up to N1, which is the left regular module. And the subquotient, so this is a filtration by submodules over our monoid, and the subquotients are by definition exactly the cell modules. Each cell module is a direct sum of modules of the form f sub f of V, because of our assumption on the characteristic of K. And so this means that the regular module Ks has a standard filtration. And of course, if F is an idempotent in S, then the kernel of the projection of the corresponding projective module Ks times F onto the cell module Kl of F is filtered by cell modules coming from strictly two-sided greater cells. That's because, as we mentioned, left cells inside the same J cell, they are not left comparable. And this completes the proof of the main theorem. Let us look at one example. Let us consider the transformation monoid T2 of the set 1, 2. This monoid has four elements: the identity E, the transposition S of 1 and 2, and two constant maps, the map C1, which sends both 1 and 2 to 1, and the map C2, which sends both 1 and 2 to 2. We have two-sided cells. The two-sided cell of the identity, which consists of the identity and of the transposition, and the two-sided cell, which consists of the two constant maps, we denote it by JC. The second two-sided cell is also a left cell, because the kernel of both these maps is just the whole set 1, 2, but it splits into two right cells, because there are two possible images. So we have the right cell of C1 consisting of C1 and the right cell of C2. The maximal subgroup of the idempotent E is S2 because we have here two elements, and this one has two simple modules, the trivial module and the sign module. Since the two-sided cell of the identity is also the left cell of the identity, the simple module, which corresponds to the identity element and the trivial module over S2, is simply the induced module Fe applied to the trivial module over S2. And similarly, the module Qe, the sign module for S2, is just the induced module Fe applied to the sign module for S2. So these two modules are in fact one-dimensional and hence simple. So we have two standard modules which are simple. The maximal subgroup, which corresponds to the constant map with image 1, is S1, because it's just one element, and this has one simple module, namely the trivial module. There is a trivial module for S1. So the induced module from this trivial module is isomorphic to the cell module for the left cell of C1. This cell module KLC1 has simple top, which is QC1, and then the trivial module for S1. And the kernel of the corresponding projection is generated by the element C1 minus C2. Because of this minus, this element generates the sign representation of S2. So which means that this kernel is isomorphic to the module Q, the identity. So the apex is now the two-sided cell of the identity, and we have the signed representation of the corresponding maximal subgroup. That's because of this minus sign. And this means that the Gabriel quiver of our algebra is as follows. So we have the vertex which corresponds to the identity and the trivial module. We have the vertex which corresponds to the identity and the sign module. And we have the vertex which corresponds to C1 and the trivial module over S1. And the corresponding projective module, which is this cell module, has this module as a top, and then the simple for the identity and the sign module as the socle. So this is the Gabriel quiver of our algebra. This is, of course, basic and hereditary, so it's clearly quasi-hereditary for any order, but in particular, it is quasi-hereditary for our fixed order, which extends the two-sided order on the apexes. So these two elements have apex JE, and this element has apex JC. This completes our example. At the end, some extra problems and questions. Problem question 1. Prove with all details that for a finite monoid S and a J cell J in S, the property Jj is equal to J implies that J contains an idempotent. Problem question 2. Prove with all details Mann-Poniatowski theorem. Problem question 3. Provide all details for the proof of the main theorem. Problem question 4. Check the assertion of the main theorem for the monoid T3 of all transformations of 1 to 3 by explicit and complete computation of all simple modules, all cell modules, and the Gabriel quiver. And problem question 5. Which commutative monoids have quasi-hereditary monoid algebras over the complex numbers? Thank you very much, and see you next time.